So welcome to the Analysis Junior seminar of today. Today the speaker is Giovanni Brigati. He's a PhD student of Jean Dolbeau at the Université Paris-Dauphine, and he talked about constructive stability for subcritical inequalities on the sphere and beyond. Please, Giovanni.
Okay, thank you very much for the introduction and also for the invitation. It is my pleasure to be here to speak to you. And let me share my presentation. I tell you that the presentation is taken from two recent works with in collaboration with Jean Dolbeau and Nikita Simonov. So you will see that I will quote the reference along the conference. So, okay, I'm Giovanni Brigati, and I work at CEREMADE with Jean Dolbeau, and I have also co-director who's Giuseppe Savare in Italy. And this project is funded by the European Union Horizon 2020 project and also by the EFI project of the French National Research Agency. So this is the administrative part, let's say, and I thank these sources of funding. So the project, as I told you, it's taken from mainly one article with Jean Dolbeau and Nikita Simonov. At the end, I will give you some highlight also on a second article, which has been recently accepted for publication. Well, the first one, this one is just an archive preprint. There's also a third work I will mention, but this is not available yet. So let me just stick to this one for the moment. So let me start with the setting and a very basic fact everyone knows. So take D bigger or equal than 1, which is the dimension of the problem. And then there's mu, which is the uniform probability measure on the sphere of dimension D. And the sphere of dimension D, you have to imagine it as it is embedded in RD plus 1. So it's just the space of vectors with unitary norm. So one fact is that if you consider the Sobolev space H1 of SD with the measure d mu, you have a continuous inclusion in LP spaces of this space. And the inclusion is continuous if and only if P of the space LP is in the range 1 to star. 2 star is, I will always call it 2 star or a critical Sobolev exponent because it's the best you can have. So I say that it's a critical value in this sense. That is the endpoint of the interval of inclusions you can have. And I will define it in 2 slides, as I say. So the first thing is that I want a quantitative version of this inclusion so that I can actually control it with a continuity constant if you want. So let me define the 2 functionals I will use along all the exposition. So there's the generalized P entropy. The generalized P entropy is the difference between the L2 norm squared minus the P norm squared divided by 2 minus P for every P different from 2. As you can easily check, for P equal to 2, it doesn't make sense. So you have to take a limit. And if you take a limit for P equal to 2, you get the entropy E2 in the second line of the display. And this is the logarithmic entropy, which is very well known, I would say, in many parts of mathematics like statistics or probability and also theory of communication, and of course, functional inequalities. And then there's the second functional I will use is the Fisher information, which is just the L2 norm of the gradient square. So I want to write this functional inequalities, which stand for the functional inclusion I explained in the first slide. So for the presentation, let me take D bigger or equal than 3, because otherwise there are some technical issues which are not so bad, but I have to distinguish the notation every time. So let me just take D bigger or equal than 3. And if you are interested in D equal 1 or 2, please check the paper. So the Sobolev exponent, the critical point of the interval of inclusions is 2 star equal to D divided by D minus 2. And as you can see, it's always bigger or equal than 2. This is important. And the inclusions of the H1 space in the LP space are written out with the GNS inequalities you have in the slides, which are the Gagliardo-Nirenberg Sobolev inequalities. GNS stands for the three authors who first discovered things about them. And the special case for p equal to 2 is included. So you also have this case, which is part of the family of inclusions. And you have three special points, if you want. You have the lower point, p equal to 1, it's a Poincaré inequality. So with respect to the uniform probability measure on the sphere, the p equal to star is the Sobolev critical inequality. So it's the best you can get. And for p equal to 2, you have that this EP, you have to take the expression E2. So you get the logarithmic Sobolev inequality with respect to the probability measure on the sphere. So these are the characterizing point. And just for the terminology, I will call a subcritical range whatever is between 1 and 2 star. So 2 is a point of the subcritical range. Even if it's a bit special, it will be included in the family of subcritical inequalities. Critical means 2 star. So as I told you, this is a family interpolating between the Poincaré and the Sobolev inequality, with the special case, which is the logarithmic Sobolev inequality. And the constant D, you see here, you have a constant D in the inequality. Fisher information minus D times the entropy is bigger or equal than 0. This constant is sharp. And if you want to check it, you have to take 1 plus epsilon alpha dot x, where alpha is any direction. And you take epsilon going to 0, you test in the inequality, and you see that this will saturate and give you D as a constant. And you have one thing that for p equal to 2 star, the inequality you get is equivalent to the Euclidean Sobolev inequality. This is not the case for all other points. Okay, this is the only one which is equivalent to a Euclidean inequality, because if you do the stereographic projection, you will get a weight. And the weight is eliminated by the fact that you are critical. Basically, you will see that you have the same weight everywhere, so you can reabsorb it, which is not the same case in the subcritical range, for example. And for p equal to star, we know that the optimal functions, which are the function realizing the constant equal to D in the inequality, are the Aubin and Talenti family, which have been computed by Aubin and Talenti in the 80s. So they are known, and they look like a reverse power of X in more or less. But the important thing is that the expression is completely explicit and known. But this is not what we are going to talk about. We are going to speak about the subcritical range. So let me restrict to P between 1 and 2 star. In this case, the Aubin and Talenti family is not anymore optimal. The only optimal points are the constants, because you can see that the critical case is special because it's conformally invariant, while the subcritical case is not. So you lose a degree of freedom, and this degree of freedom disappears and gives you just the constants, while in the critical case, this degree of freedom helps you to pass from the constant to the Aubin and Talenti family, and all of them are included, because if a constant is optimal and the inequality is conformal invariant, also conformal transformation of the constants are optimal functions, and those are exactly the Aubin and Talenti family. And as we will see, these subcritical inequalities have a strong connection with the diffusion flows. So what's the main question? The main question is that if you take the deficit functional, which is let's say the difference between the two sides of the inequality, so it's the Fisher information minus the entropy, the inequality says that this deficit functional is positive or equal to 0, and it's equal to 0 if and only if f is a constant. Okay, this corresponds to optimality. You have if you have this functional which is strictly positive when your f is not a constant, you want to understand if this functional is a measure of how much f is not a constant. So because you will see a positive quantity, and you want to know if this positive quantity will control some way the fact that f is not a constant. So what we are going to ask exactly is if the deficit controls some distance from the optimal functions, which are the constants. So you have this expression where the deficit controls a constant times some distance between function f and the optimal family f star to a power q. And all these things are very important. The distance, because you want the strongest possible one. You want to know how much you are not a constant in the best possible sense you can control, which is the h1 distance you will see. Then you want the sharp exponent q, because you want to know exactly how the deficit goes to 0 if you go close to a constant. If I take an f which is closer and closer to f star, I want to know this q because it tells me how the deficit goes to 0. At least it's an estimate. So I really need this. And the best thing this in the literature is called explicit result. If you have the distance, which is the strongest possible one, and the q, which is sharp in the terminology introduced by Alessio Figalli, you have that this is an explicit result. Then you can do more. If you can also quantify the constant small c in front of the distance, you will have a constructive estimate. So what I'm going to do is provide you with the best possible distance, sharp exponent q, and a constructive constant c, so that I will have an explicit expression at the end. So this is what I'm going to do. And of course, we didn't start from scratch. There's a long history about this kind of facts. So the Sobolev Gagliardo-Nirenberg inequalities come from the first half of the 20th century by their works of these authors. And for the critical case, we know that the optimal functions have been computed by Aubin and Talenti, as I told you. So this is the, let's say, old story. Once your inequality is optimal, you can ask if it's stable. So the question I asked in the slide before, this one makes sense only if you know the optimal constant and the optimal functions. Otherwise, you are speaking about nothing, because the term f star in the inequality is unknown, and also the deficit is not written out properly, because you really want to have the good constant in front. Otherwise, it doesn't make sense. And so this is needed. And the first people asking for stability of this kind of inequalities were Brezis and Lieb. And a partial answer for Sobolev's inequality was given by Bianchi and Egnell, and they computed a result as the one in the slide before, just for the critical case, with the best possible distance and the sharp exponent q, but the constant c was unknown until a recent paper by Dolbeau, Esteban, Figalli, Frank, and Loss, where they also construct the constant. So it's a true advance, because you pass from the explicit to the constructive estimate if you want. And for Gagliardo-Nirenberg Sobolev inequalities on the Euclidean space, so they are not on the sphere, on the Euclidean space, you have also a paper by Bonforte, Dolbeau, Nazaret, and Simonov, where there's some constructive stability under some additional hypotheses. Typically, you have to control the tails of your functions at infinity, and you can do something. So this is for the Sobolev inequality, if you want. And for the subcritical range, these inequalities have been written by Didot-Véron and Véron on the sphere, and then they have been taken again by Beckner in the 80s and in the 90s. So it's quite recent. And some improvement were made by Dolbeau, Esteban, Loss, and co-authors along the 2000s. And some links with the Hardy Littlewood Sobolev inequalities have been established by spectral methods by Frank and Lieb. And then we come to the state of the art, which is the most recent paper in the field, which is a paper by Rupert Frank in 2021, where the first true stability result for the subcritical range appears. So let me, okay, here I reviewed a bit the case for p equal to star. So you have a bit of history more in details, but I really want to skip this part and go to the subcritical range. So for the subcritical range, as I told you, not so much was known. The first true stability result is due to Rupert Frank in 2021, but there were some nonlinear improvements by Dolbeau and Esteban and Loss, and I will present something about this later on. So here you see that if you read this inequality, I will give more details afterwards, but if you see this inequality, you have that the Fisher information doesn't control d times the entropy, but d times a function of the entropy. And this function is slightly better than a line. So you control slightly more than the entropy. And this is not a stability result, but it's an improved inequality. So it goes in the same direction. You add some extra term to the inequality if you want. And okay, what I'm saying, as I told you, in the subcritical range, the optimal functions are the constants. So the distance I'm taking is just the L2 norm of the gradient. Why? Because I want to measure the H1 distance, but the H1 distance on the sphere is equivalent to the L2 norm of the gradient with the Poincaré inequality, of course, with the average taken out. But the average here doesn't play much role because the optimizers are constants. So with this gradient, I will measure 0 for the constants. And so this is the natural distance I will use. This is really a distance on the sphere. So now let me go to the state of the art. So I told you that the first stability result for these inequalities arrived with Rupert Frank, and this is the result of Rupert Frank. He proves that the deficit of the inequality, if you want, so the Fisher information minus d times the entropy, controls a constant which depends only on d and p, and you have a gradient to the power of 4. So don't look too much at the denominator. The denominator is just a normalization factor, which is useful to keep the true homogeneity of the inequality. But if you take a function which is really, really close to a constant, so the gradient is small, this denominator will be close to a number. So will be close to 1, for example, if you normalize the things properly, and you will see a gradient to the power of 4. So the message you should keep of this estimate is that the deficit controls the gradient to the power of 4, okay? And Rupert Frank did it only in the range between 2 and 2 stars, so between the logarithmic Sobolev inequality and the Sobolev inequality. But as you will see, we will be able to say the same for the other functions in the family of for the other functions inequality in the family. But for the moment, we see that we have this exponent 4, which looks bizarre because in the Sobolev inequality, so the critical case, you have that the exponent is 2 because Bianchi and Egnell computed it, and also we have the constructive result of Delbo, Figalli, Frankenstein, and Loss. So we are sure that it's 2. But here you see that there's a 4. So the first reaction was this result, maybe it's suboptimal, but Rupert Frank says that if you take this sequence 1 plus epsilon alpha dot x, indeed the exponent 4 is sharp. So this result is degenerate. In the critical case, you control a distance 2, but here you control a distance to the power of 4. So something is going on. And we know that the two results are correct. So there's a true difference between them. And the other things I want to say is that the constant is unknown. So the C Frank dp is got by compactness with concentration compactness argument. So it's never known. You get it by contradiction. So you have 0 estimates on the value of the constant, but you know that it's positive. This is true. And so the first thing we try to do is saying, okay, what if we look at the inequalities in a spectral way? So let me skip a slide. I go to the proof and then I go to the results, but it's just because I want to tell you that on the sphere, we have the spherical harmonics decomposition. So you can take a function and decompose it along spherical harmonics. Spherical harmonics are the eigenfunctions of the Laplace-Beltrami operator on the sphere. So they play the same role as modes in a certain sense, and they are an orthonormal basis for L2 and also for H1. So you can decompose a function on a spherical harmonics, and you can write this Funk-Eke formula, which says that the P entropy is less or equal than these coefficients Zj of P times the decomposition on the spherical harmonic of degree J. Okay, And these coefficients are completely explicit. We can compute them. And this version of the Funkeke formula is due to Funkeke, but indeed it was rewritten after some decades by Lieb, by Beckner, and also by Frank and Lieb in the 2000s. So keep in mind this formula, and this formula is a proof of the inequality. If you write the coefficients correctly and you estimate them, you will have a proof of the inequality. So our first reaction was, what if we eliminate one coefficient in this sum? Do we get some improvement? For example, if you think of the Poincaré inequality on an interval and you eliminate the first frequency, you will get an improved Poincaré inequality because you eliminate the optimal function. So this was a bit the same idea, to say, yeah, what if we eliminate one eigenspace of the Laplacian? What do we get? And now I'm telling you what we get. So first theorem of our paper: if you take a function on the sphere such that you are orthogonal to the first eigenspace of the Laplacian, then you will have an explicit control in the stability. So the deficit, okay, this is written for the logarithmic Sobolev inequality, but in the next slide I have it also for the rest of the family. Just have a look at it in the logarithmic Sobolev inequality. It's the same. So you have that the deficit of the logarithmic Sobolev inequality controls a constant, which is very explicit. It's 2 divided by d plus 2 times a gradient to the power 2. So this is already a bit different with respect to what Rupert Frank did, because Rupert Frank says that here you have a gradient to the power 4, and here we have a gradient to the power 2. And as I told you, this normalization term in the estimate of Frank, imagine that it's equal to 1, that you are very, very close to the manifold of optimizers, so that you see actually just the gradient to the power 4. Here you see gradient to the power 2. So this result is indeed better than the one of Rupert Frank, but under the orthogonality constraint 1. So the estimate of Rupert Frank is general. This is just on a subspace, if you want. And here I show you the same for the rest of the family. So if you take P, which is different from 2, it's between 1 or 2, or between 2 and 2 star, and P equal to 2 is in the other slides. If you take the orthogonality condition 1, which is always been in the complementary of the first eigenmode of the Laplacian, you get an explicit improvement. And the constant is known, and the exponent 2 is sharp. And the proof, now I come back to the proof. So I told you that in the Funkeke formula I wrote there, you eliminate one mode, so you expect to improve it. And this is the case. So you get a better coefficient for the mode 2. And then you see that these coefficients are increasing, and you have also some convexity properties to use to make estimates. So basically the important coefficient is the first non-zero coefficient you have. So if the first non-zero coefficient you have is 1, you just get the basic inequality. If you eliminate the coefficient 1 because you have an orthogonality constraint, then the first coefficient is 2, which is better than 1, and it's also controlling all the other ones. So you get the improved version of the inequality. And the thing is that if you keep the coefficient of j equal to 1, you get nothing. You just get the inequality. If you want, this is a proof of the inequality. So some comments on this, that you have no improvement for the critical case. If you try to do our proof for the Sobolev inequality, you get that all coefficients are equal to 1. So there's nothing to do. And you can ask, okay, in the subcritical range, you told me that you eliminate j equal to 1 and you improve. What if I eliminate j equal to 1, 2, 3, 4, etc.? You get an improvement, and it's explicit because the coefficients are decreasing. So if you eliminate more and more coefficients, you will get better and better constants. And as I told you, there's no contradiction with the result of Rupert Frank, because Rupert Frank gives a global result, so no constraint at all. It's good for all functions. And we have an improvement, but under orthogonality constraints. So there's no contradiction, but one can say, yeah, this result of order 2 is good everywhere except in the first eigenspace of the Laplacian. And if you see the sequence given exponent 4 in the proof of Rupert Frank, it's 1 plus epsilon alpha dot x, which is exactly in the forbidden space. Okay, so you see the result of Rupert Frank uses exactly the sequence we forbid to prove order 4. And once you eliminate this sequence, you get order 2. So the natural conjecture is to imagine that the degeneracy from order 2 to order 4 is created by just these sequences, okay? If you have only the component on this first eigenspace is the bad one, and all the rest of the H1 space is a good one. And this is true. So let me give you the second result of our paper, which is written always for the logarithmic Sobolev inequality. You have also a slide with the Gagliardo-Nirenberg. So for the logarithmic Sobolev inequality, let P1 be the projection on the first eigenspace. So you take a function and you decompose it as P1f plus 1 minus P1f. And this is exactly the spirit of our result. And the result says that the deficit in the logarithmic Sobolev inequality, for example, controls with a stability constant SD, which is explicit, it's constructed, and I will show you how to build it. You have a power 2 in the distance if you are in the orthogonal space. And if you are, let me call it the parallel space, if you are in the eigenspace generated by X, which is the space where you go if you apply P1, you will have gradient to the power 4. And this closes the gap between our results and the theorem of Rupert Frank, because if you don't put any condition, the exponent 4 will win. But if you eliminate the parallel component, you will get the exponent equal to 2, because you are in the space identity minus P1 if you want. So this is the complete picture in a certain sense. And you have the same for the Gagliardo-Nirenberg inequalities. So if you are in the subcritical range, but you are not the logarithmic Sobolev inequality, you have the deficit associated with the Gagliardo-Nirenberg, and you will control with the constructive constant the power 4 of the distance in the parallel component and the power 2 of the distance in the perpendicular component. Perpendicular and parallel with respect always to X, if you want. And so I would say that this gives you more or less an idea of what's going on, that the degeneracy is localized in just in an eigenspace, and in all the other subspaces you don't have any degeneracy. And this degeneracy in the critical case is not there, because in the critical case the P1 space will be part of the optimizer, so it will be absorbed in the left-hand side of the inequality, and you will see just the gradient to the power 2. So now I will use the last 15 minutes or whatever to prove this result for the Gagliardo-Nirenberg inequalities. And the log Sobolev is just taken as a special case. Nothing is different, just the expression of the entropy, which contains the log. So with the derivatives under the sign of integral, we should pay a bit more attention, but it's basically the same. So what's the strategy and what are the techniques of the proof? Usually in stability results, you do a local stability estimate with the Taylor developments. So Taylor expansion, sorry, development is in French. But okay, you do Taylor expansion locally, and you control explicitly the remainders. And here there's one more difficulty, because the first eigenspace will be messy, because you see that it's all the matter of the subject at the end. So we should keep it carefully. And this is an idea of Rupert Frank, indeed. We made it constructive, but the idea of keeping a special eye on the first eigenspace comes from his paper. And then there's a local to global argument. So you prove the estimate when the gradient is small, if you want it with the gradient big, usually the state of the art is to use a concentration compactness, so a contradiction argument if you want. But here, if you want a constructive constant, you can't use a contradiction argument because it will never give you an estimate. So here we will use nonlinear diffusion flows. If I am very far from being a constant, I will jump a bit on the diffusion flow, and the diffusion flow will naturally drive me towards the constants. And once I'm close to the constants, I use the local stability. This is the strategy. So it's a bit the contrary of what's usually done, so that you prove it locally and then you go local to global. Here, indeed, you will go global to local and then prove it locally. It's a bit the converse, because since the strategy is constructive, you have to start with the, let's say, with the bad case and then do careful computations on the good case, which is when you know that already that you are close to a constant. So the good of this method is that it's fully constructive, no compactness at all. And the second thing which is good, which is a bit more subtle, is that we use the same flow to prove the inequalities and to prove the stability. You will see it. And this is a difference, for example, with the paper of Dolbeau, Figalli, Frank, and Seban and Loss, because they use a symmetrizing flow to do their estimates, and the symmetrizing flow is not the natural one. The natural flow is the fast diffusion. So here we are on the sphere, which is compact, so it's a bit easier, and we can actually use the fast diffusion flow, which is the natural one. You will see why. So keep in mind, this is the general picture. Now we'll go in the details. So I promised you a flow. I show you a flow, which is on the sphere, this kind of object. So you take that the time derivative of solution Z is the Laplacian of Z to the power M. I told you that the flow is nonlinear. So if you take M equal to 1, you are linear, but you can also take an M which is not necessarily 1. And this is useful, you will see, because if you have only M equal to 1, you are not so happy. You need some freedom in the choice of M, and I will show you where's the freedom. So for convenience, let me take the P square root, the P root of U in, I misspoken. Let me take U as the 1 over P power of Z and rewrite the flow 4 in another way, which is the flow 5 you see here. So now, what do we do with this flow number 5, which is a bit more messy, but it's the same, just a change of variables. So what we know is that if you take P, which is between 1 and 2 star, and all dimensions D equal to 1, you have N minus and M plus, such that if you take M between M minus and M plus, where M is the same here, okay? It's a measure of your nonlinearity. Then if you take M, which is good enough, you will have that the deficit of the inequality will decrease along the flow, and the Fisher information will go to 0. So the combination of these two things prove the inequality. If you take the derivative of the deficit is negative and you integrate it in time, you get the Gagliardo-Nirenberg inequality for the initial data. So this is another proof of the Gagliardo-Nirenberg inequalities if you want. And pay attention, because the linear flow, which is the heat equation, is not always possible. So I put a figure in the previous slide. Now it makes sense, because in this figure, which is for D equal to 5, you see that on the horizontal axis, you take the P family. So you go from 1 to the Sobolev exponent, which is a bit bigger than 3. And then in the vertical axis, you have the admissible M. And you see that if you are very close to the Sobolev exponent, the M equal to 1 is outside the gray region, which is the good family. So you can't use the heat equation every time. You really need to use this nonlinear diffusion flows, okay? So this is just to motivate the fact that I use the this kind of flows, not just for technical purposes, but because it's necessary. The heat equation won't do the job. So I take this nonlinear diffusion flows and I have these properties. So now I have to be more careful in the calculations. And without loss of generality, let me take the L2 norm of F equal to 1. The inequality is too homogeneous. I have a degree of freedom and I will use it. So I use to fix the L2 norm. And if you do a careful computation along the flow of the nonlinear diffusion I put in the previous slide, you will see that the derivative of the deficit less or equal than 0, it's too pessimistic. You can have an explicit expression, which is not exactly the derivative, it's an estimate of it, but it's some negative contribution. You see, this gamma and beta are complicated numbers you will find in the paper, which depend only in the on the dimension and on m. And you can have a real, let's say, an effective estimate of the derivative of the deficit with this v, which is not exactly u, but it's a power of u. This is just a way to write it in a way that it's a quantity related somewhat with the Bakry-Emery computations. You will have this term every time. So it's important to write it like this. And so if you have that the derivative of the deficit is less or equal than 0, and you integrate, you get the inequality. If you have also this negative contribution, you can, by interpolation, and this is an idea by Demonge, you have to check in his PhD thesis, you will have an improved inequality. So you will have that the Fisher information controls a function of the entropy, not just the entropy. And the improvement exactly comes from this additional term, I neglected, because if you neglect, you get that phi is equal, you get phi equal to the identity. If you also take into account the negative contribution in the derivative of the deficit, you will have a phi which is a bit better than a line, okay? And if you rewrite, this is written in terms of the entropy, but if you rewrite the things in terms of the Fisher information, and this is done with a Legendre transform, you will get a sort of nonlinear stability estimate. So you have that the deficit, this is the last formula I have here, the deficit controls some function of the gradient, where psi is known, you can compute it. It's not so easy because it's the solution of an ODE, but at the end we will get an explicit expression. And so the deficit controls some nonlinear function of the gradient. But this psi is convex, increasing, and is 0, and also have the 0 derivative in 0. So if you develop this psi to the order 4 using a Taylor expansion, you will get the estimate of Rupert Frank with the gradient to the power of 4, but the constant is explicit. So it's an improvement. And the second improvement is that using convexity, if you are far away from the optimizers, so that let's say the gradient is much bigger than, it's not much bigger, it's bigger than a parameter theta to fix against the p norm squared, you have the stability. This is done just by convexity. If you, in the expression of psi, if you multiply and divide by theta, you can prove this result. You can prove the stability in the faraway regime. And you see that this is a far away from constants because if f is close to a constant, the left-hand side is 0 and the right-hand side is big. So if you are far from a constant, it's the converse. You have that the gradient is big with respect to the LP norm. Now, and we can do this for any theta. So take theta as small as you want, and now we reduce to the other case when the gradient is very small. So the gradient is less or equal than a constant times the p norm, if you want. So here, what do we do? If you have that the gradient is smaller than a constant theta times the p norm, you can prove, since you are on the sphere, using the Poincaré inequality and using the fact that I fixed the L2 norm equal to 1. This shouldn't be forgotten, that the gradient is small. So with a smaller than a constant theta prime, which is roughly speaking, theta. They have the same order. It's not exactly the same, but they go to 0 with the same speed. So more or less they are the same. So this is the first step, saying that the gradient is actually small. Then you take a control on the average, and this is done just with the Jensen inequality on one side and with the Poincaré inequality on the other. So you see that the average square is close to 1 as much as you want. So now you take the function and you develop it along spherical harmonics. There's the 0 degree spherical harmonic, which is the average. Here I cheated a bit, I put 1, but if I take theta small enough, I can take the first term in the expression of f close to 1 as much as I want. So it's cheating, but not too much. And then there's the projection on the first spherical harmonics. So I call epsilon, it's the coefficient, and then there's this x dot alpha, which is the spherical harmonic of degree 1. Then there's plus eta, which is the coefficient I put in front, f perpendicular. So f perpendicular is all the other modes. You have 0 mode plus mode of order 1 plus all the rest. And epsilon and eta are fixed so that all the coefficient, sorry, all the components have H1 norm equal to 1. You see that the gradient of f perpendicular is equal to 1, and also the gradient of x dot alpha is equal to 1. It's just a normalization. And since the sphere and all the problem are rotational invariants, just for simplicity, I will take that alpha is equal to the first direction. It's the first canonical direction. This thing I can always do, because otherwise I can rotate everything and get it. And note that since theta prime is the L2 norm of f, of the gradient of f, sorry, epsilon square plus theta square is less or equal than this theta prime that is as small as I want. So now I tailor a develop relay, and I take the L2 norm of the gradient. If you do this L2 norm, you get the gradient of 1 is 0, of course. Then you have the gradient of x1 square, but x1 is an harmonic of order 1. So it has the property that its norm of the gradient squared is equal to d. Okay, so you get epsilon squared times d. And then since we normalized the norm of the gradient of f perp equal to 1, we get this eta squared. So this is the Taylor development of the H1 norm. Then there's the L2 norm, which is very simple because the composition is orthogonal in L2 and in H1. So the development of the L2 norm is just 1 plus epsilon squared plus eta squared f perpendicular to the power 2. But now remember that in front of the L2 norm, there's a coefficient d, okay? Because it comes from the deficit of the inequality. I go just back to the first slides that here. You see that you have this coefficient d in front of the entropy, so in front of the L2 norm. Now I go again to the calculation, and okay, so in front of this L2 norm, you have to imagine that you have a d. So in front of this epsilon squared, there's a d. And you have it in the L2 norm of the gradient and in the L2 norm. So there's a cancellation. And here you see by hand, while the result of Frank has power 4. Because if you imagine that eta is equal to 0, so you have just a sequence with epsilon. Here the second order term in the Taylor extension vanishes because you have a cancellation. And so you hope that you have epsilon to the power 4 in the Taylor expansion of the P norm, but this term will be absorbed. And in the Taylor expansion of the LP norm, you have another epsilon square, but here I did a mistake. This epsilon square combined with the one of the L2 norm divided by P minus 2 and multiplied by D cancels out the D epsilon squared in the first line. Sorry, you have also to take into account this one, but all of them, they cancel. The message is the same. The term in epsilon squared goes away. So you lose it. Then you have a P minus 1 term eta squared with the f perp squared, and then you have a term with the epsilon to the power 4 and a positive coefficient in front. And this is the good term because it will give you the fourth power in the gradient of the parallel component. And then you also have a sort of cross product. So you have epsilon to the power 2, eta, and then you have f perp against the first eigenmode to the power 2. So if you put all together, in the expansion of the deficit, you have eta squared times a positive coefficient, because if you take just the f perp component, you will be orthogonal to the first two eigenmodes. So you will have an improved Poincaré inequality that says that if the gradient is equal to 1, then the L2 norm is strictly smaller than 1 over 2d, for example. So there's a positive coefficient in front of eta squared. There's also positive coefficients in front of epsilon to the power 4. And then you have this cross product. And the cross product contains the coefficient of f perpendicular along the second order spherical harmonic x1 squared minus d plus 1. But if you complete the square using the Young inequality, you can reabsorb this term. And then you have lower order terms. You can estimate them explicitly. So at the end, the message is that you will get that the deficit controls a constant C1 eta squared plus a constant C2 epsilon to the power 4, which corresponds to order 2 in the perpendicular component, order 4 in the parallel component, plus some remainders, but the remainders are small o of this term, and if you take epsilon and eta small enough, you can control everything, and you can do, because epsilon and eta are less or equal than this theta prime is the same order of theta, and theta, you can choose it as small as you want using the nonlinear diffusion flow. So this is the end of the part on the sphere. Let me just 3 minutes to advertise the new results. So there's another paper we did in 23, which is on Gaussian interpolation inequalities. So it's not directly linked with the sphere, but you will see why. Because it's a general understanding, which is a very old story taken from papers by Poincaré, Maxwell, and Meller. So it's more than 1 century ago that the sphere in a large dimension with a uniform probability measure looks a lot like the Gaussian space. I think that in the paper of Poincaré, he was doing calculation with the spherical harmonics and proving convergence to Hermite polynomials with the dimension going to infinity and a good scaling. And also in Meller, this is in the 70s of the 19th century, you will find the same. And Maxwell arrives more or less to the same conclusion, but with an argument taken from kinetic equations about the distribution of some particles in the kinetic theory of gas. And Beckner in the 80s takes again this kind of argument to somewhat prove convergence of Gagliardo-Nirenberg inequalities to interpolation inequalities in the Gaussian measure, which nowadays are known as Beckner inequalities. But the approach was not so rigorous. So the first goal of the new paper we wrote is to make the convergence of the Gagliardo-Nirenberg inequalities on the sphere to the Beckner's inequalities in the Gaussian space fully rigorous. You will see how. And with one attention that the exponent 2 star, 2d divided by d minus 2, goes to the number 2 as the dimension goes to infinity. So the Sobolev's inequality, the critical case, will converge to the Gaussian logarithmic Sobolev inequality, because the exponent equal to 2 gives always the logarithmic Sobolev inequality. So the logarithmic Sobolev inequality, which in the sphere is subcritical, becomes critical. And it's also the critical point of the infinite dimensional family. So it's, I would say, the worst of the worst of, or the best of the best, as you, depends on how you see things. But the message is that this is still very difficult. So we are working on this point. But we have quite a good theory for the subcritical range. So let me present you what we have for the subcritical range in the Gaussian space. which is the range between 1 and 2. So this is the convergence result, which says that if you rescale the spheres properly, you have that all the compactly supported function in the Gaussian space can be approximated with functions on the sphere in the sense that the deficit of the Gagliardo-Nirenberg inequalities will converge to the deficit of the Beckner's inequalities on the Gaussian space. So if you want, this is a pointwise convergence result. You fix a function v in the Gaussian space, and you can write a family of functions on sphere of increasing dimension, which will such that the deficit in the sphere will converge to the deficit on the Gaussian space for your original function v. So this is the first completely rigorous argument of convergence of spheres to the Gaussian space with respect to functional inequalities, which makes, let's say, completely effective the setting of Beckner. And it's a rigorous point in the intuitions coming from Maxwell, Meller, and Poincaré himself. So you also have a convergence result for flows. You remember this is the picture of the nonlinear diffusion flows which are compatible with the Gagliardo-Nirenberg inequalities. On the horizontal axis, you take an exponent of the Gagliardo-Nirenberg inequality, and in the vertical axis, you have the exponent of diffusion flows which are compatible. And this region, you can compute the limit, and you get this egg. And this is the figure you have in infinite dimensions. So if you take the deficit of the Beckner's inequalities, and you take a nonlinear diffusion flow where the Laplacian is substituted by the Ornstein-Uhlenbeck operator, which is the infinite dimensional version of the Laplacian, if you want, and you do this, you do the diffusion of the you do the variation of the deficit along the diffusion. You see that the exponent of the diffusion where you have that the deficit is decreasing are exactly the points in this figure. And this figure is the limit of the finite dimensional figure. So this is a sort of continuity, if you want. The figure in d equal to infinity is the limit of the figures in finite d. And then the last result, and then I leave you, is that, okay, we don't have spherical harmonics in infinite dimension, but we have the Hermite polynomials, which are more or less their infinite dimensional version. And you have the same phenomenon. So we prove a constructive stability result. If you take the deficit of the Beckner's inequalities in the Gaussian space, you will control a power 2 on the orthogonal component with respect to the first order Hermite polynomials. And in the bed subspace generated by first order Hermite polynomials, you will get the power 4. So it's exactly the same. And I thank you again for your invitation and also for your attention. And I stop here. Thank you very much.
Thank you, Giovanni. So if anyone has a question, please. Also online. Well, it seems that you have been very clear, Giovanni. So I think that we can thank Giovanni again. And Simone has a question.
If you have some relevant example and some application of this inequality, especially the first one of your result with the exponent, the better exponent, some I don't know additional problem that you can solve with this inequality. I don't know if there are any problems.
One problem you can solve is always to understand better fine properties of the diffusion flows on the sphere, because this result, if you read it in a flow fashion, says that the the parallel component will converge very slowly to the constant, because imagine that you take the heat equation. Imagine that you have really the logarithmic Sobolev inequality, and you take the heat equation on the sphere, so that you are the two are compatible, because the point logarithmic Sobolev inequality and m equal to 1 is always in the region in the picture here. So imagine that you are in this case. One thing you can say is that, sorry, go to the inequality. One thing you can say is that if you take just the parallel component, you will get the slowest possible convergence rate to the constant, because on the sphere, the heat equation has only one equilibrium, which is the constant. So if you take any function, it will become its average after for the time going to infinity. And you see that you can compute the sharp speed of convergence, and it's given by the parallel mode. Sorry, I was referring to this. And then you also have another effect, which is not so predictable, that is that the orthogonal component will converge to the parallel component in a faster time scale, because the slowest time scale is the convergence of the x to the average, but what is not parallel will converge faster. So if you want, you can have improved convergence rates. This is an immediate application I have. So if you have improved decay rates for the heat equation, you can imagine that in many systems of physical interest, where one part is given by the temperature, if your initial datum is good enough, for example, is orthogonal to x, you will have an improvement on convergence rates.
Okay. Okay, thank you.
You're welcome.
Any other question? Okay, so let's thank Giovanni again. And I don't know if next week we have another speaker. Do we? Maybe.